Good. Questions on action graded? Okay. We have kind of an assembly of concepts, really small, like breadcrumbs that we need to cover. I'm trying to think what to leave because I don't have probably. Okay, you kind of have a brain image here. What's going on? Okay. So first thing that, and these two periods, absolute and refractory, they basically make sure that your action potential travels one way. Now, the idea, the concept of saltatory conduction. So what is that? Imagine that this is a neuron. Basically the axon. It's just the cell, okay? This is another axon. Right? Two axons, okay? So now look at the graph and tell me which channels you gotta open to make a full depolarization. Sodium channels, right? And they depolarize in order to open adjacent sodium channels. You see what I'm saying? And adjacent. So, let's say you have sodium channels here. They will produce local depolarization, but these electrical charges will be constantly leaking out. I mean, it's not insulated axon. So you need to position next sodium channel very close, and next one very close. And they should be pretty closely located. Got it? Now, let's do this. Let's put sodium channel on this neuron here, and then let's slap a myelin sheath, which will prevent leaking of the charge, which will electrically insulate. Does that make sense? So depolarization now can be extended through the all myelin sheath. Okay? So next sodium channel, you can put it here, and then you slap another myelin sheath, and you put it here, and then you slap another myelin sheath, and you put it here. So I just counted, I have 10 sodium channels on top neuron, and I have 4 on the bottom. So in order to go from point A to point B on myelinated neuron, I have to open substantially less sodium channels. So in terms of the speed of transmission, which one will be faster? Which one? You need to open 10 doors instead of 4. You need to run through 10 doors, opening them one by one, instead of running through 4 doors. You see the difference? So, myelinated neurons transmit signal faster. Non-myelinated slow. I'm trying to do a little bit of a maybe clinical connection here again. The example that I did, if I will throw my keys at Tyrone, would you be able to catch him? If I'm not gonna like slam, but if I will, yeah. So, look, his response will be really fast. He will have to see them, understand the direction, and extend the arm to grab them, right? Now, when I tell you things, when I tell you words, you either understand, well, you understand the words, and then you understand the concepts, or you don't, which is fine. And that happens right away. Like I tell you something, right, and then Kui says, I don't know. Or Miranda asks the question like, I don't understand what's this, right? This all happens very fast. Those are your myelinated neurons. You need this to be fast. You need your skeletal muscles to be fast. You need your thoughts to be fast. See that? So, majority of somatic neurons, the ones that voluntary, they myelinated heavily. Neurons that control your organs, very little, if any, myelination. Because come on, who cares if signal goes from your brainstem to your stomach in 2 seconds versus 5 seconds? You know, it's not a big deal, right? Nobody needs the response to be that quick. Good? So, what is saltatory conduction? Basically, saltatory conduction is the movement of action potential between the nodes of RNVA. Okay, action potential moves from one node of RNVA to another. There's a gaps in myelin sheath. Okay, we're good?
This air is messing with me.
Say again?
The air is messing with my allergies really bad.
Is it dry?
It's just, I don't know. It's horrible.
Seasonal allergies. Okay, so far, that saltatory conduction concept. Make sense? Now, we're going to throw a couple of terms. And then we're going to talk about how we can reach the threshold again. First of all, let's say, imagine you have a neuron with 200 dendrites. It's pretty common. Okay? There's multiple, typical multipolar neuron with multiple dendrites. There's a synapse in each dendrite. There's so much neurotransmitter is released, okay? And what this neurotransmitter does, it produces that little graded potential. Okay? That makes sense? So one synapse, usually the depolarization that this graded potential that's produced in one synapse, it's not sufficient to reach the threshold. So this little excitatory postsynaptic potential is, the acronym is EPSP, excitatory postsynaptic potential. Okay? Little depolarization on the synapse. Does that make sense? Now, if you have those tiny depolarizations on many synapses over a long period of time, can they add up? Why not? Sure can. Okay? And when multiple excitatory postsynaptic potentials start to add one on top of another, are you following me? You can reach the threshold. Good? What if, check this out, what if instead of sodium influx, you have chloride influx? You're going to have inhibitory postsynaptic potential. Does that make sense? So, now imagine a neuron that receives two signals. One is excitatory, like this. One is inhibitory, like this. What's going to happen to them? They're going to do what? Somebody says you do this, and somebody says you don't do this.
Cancel.
Yeah, they cancel. This is kind of, this is what can happen to a signal. Signal can be amplified, can be maintained the same, can be cancelled, okay? It's on synapse, everything can happen. Good? Now, how excitatory postsynaptic potentials, how can they be added up? This idea is called summation. We have summation, circuits, and zones, and that'll be it. So imagine that your car got stuck in the snow. Okay? You put it in neutral, you decide to get it out by yourself. Maybe it's not a truck, like maybe it's like Ford Focus, okay? Small sedan. So get out, it's in neutral, no parking brake, you get behind it, and you push it and just go away. Think that's it. It's probably not going to help, right? It's not going to help. Unless you like a mountain from Game of Thrones, it's not going to help. But then it's not a Ford Focus. So what you're going to do, you're going to push it once, it's going to move forward, and then you're going to push it more and more frequently, right? Trying to kind of superimpose those efforts, and you will get you'll get it out of the snow. So this is the analogy of multiple excitatory postsynaptic potentials arriving with a high frequency over time on the same synapse. Okay? It's called temporal summation. Many EPSPs, high frequency, over time, same synapse. Okay? And what is the alternative way to get your car out of the snow? Ask a couple of strangers to help you. So you all get around the car, right? A couple of people behind the trunk, a couple of people at the front passenger and driver's front doors. And you say like 1, 2, 3, and you'll push together. So this is called spatial summation. From the space. Many PSPs, again, different synapses, same time. So far, questions? Okay. Any questions on the summation? Basically, you have to match the description and the term. That's one of those things. Last couple of things for that chapter. Know for types of neuronal circuits. They are in the lectures. There's a divergent, convergent, reverberating, parallel after discharge. There's a copious explanation for each. Basically, in divergent circle, one neuron sends the signal to them. 2, 3, they send, each of them sends to 2, 3, 2, 3, 2, 3, like general commands to the colonels to majors, majors to lieutenant, captains, captains to lieutenants, and like it spreads and spreads, and eventually it reaches sergeants, and the entire army knows the will of one person at the top. Make sense? That's the divergent circuit. It usually regulates motor activities. Convergent circuit will be the opposite. Like you have, I don't know, reconnaissance officers, they give the reports to smaller number of officers, they give report to smaller, and it all comes down to a single general at the top. So many neurons to smaller number of neurons to smaller, they converge. Mostly sensory information, okay? Reverberating, they organized in like circle. They produce repetitive movements, okay? Not only blinking, but also walking will be controlling, okay? Parallel after discharge, higher processing of information, like thinking, analysis, mathematical calculations, stuff like that. Good? Just general knowledge. We're not going into the woods there, okay? And zones, there's a slide talking about discharge and facilitated zone. I usually use that for the example. I say, I am presynaptic neuron, and you folks all postsynaptic neurons, okay? So let's say Lisa and Kui are in the discharge zone, and these groups of folks are in facilitated zone. So when neurotransmitter gets to you, Lisa so when I communicate to them, there is a full-blown action potential in them. They keep transmitting the signal. This is why it's called discharge. What happens in you folks? You receive a PSP. You receive enough neurotransmitter to come a little closer to the threshold. You become facilitated. You're not there yet, but you facilitated. Maybe some other signal from another neuron will get you to fire up. Does that make sense? That's all. For, like, we're done with neurophysiology, which is electrophysiology, which is great. Questions? Okay.